Hello, everyone. Thank you for coming out to today's lecture from Luce Professor of Complex System Studies, Dr. Peter Airdy with the Department of Neuroscience and the Department of Complex Systems. Today's lecture will discuss the work of John Hopfield and Geoffrey Hinton, the recipients of the 2024 Nobel Prize in Physics, as well as the history of artificial intelligence and its impacts on today's society. Please join me in welcoming Dr. Peter Airdy.
Thank you, Viv. I'm very happy to see you here. So when I heard that the Nobel Prize for Physics went to John Hopfield and Geoffrey Hinton, it was obvious and it came to my mind, I would like to give a lecture. Why? Number one, it gives me a good opportunity to prepare this lecture. Obviously, it is not a canned lecture. In my age, I have many canned lectures. But it's something new. I try to think on it, what did they do, and how to put it into a historical context. And the idle time is a little... So, the title of the talk is Interdisciplinary Science, Neurophysics, and Learning Machines. Please note, not machine learning, learning machines. And at the beginning of the lecture, I would like to express my gratitude to a number of students who established an interdisciplinary fund for complex system studies, initiated by Beth Flower and a couple of other students who graduated, believe it or not, in 2009. And it's not a shame. Tell your parents donations are always accepted. And so, what is the topic? So the Nobel Prize in Physics went to John Hopfield, who is now 91, and Geoff Hinton, he is in my age. And they were awarded jointly as a formal text, right? For foundational discoveries and inventions that enable machine learning with artificial neural networks. And so some of my hardcore physicist friends, why? Why to give a Nobel Prize for these guys who might have been something very important for the neural network, but it is not hardcore physics. Among others was János Bergó, my friend who was here in the spring and gave the Tortolet lecture. Peter, is not physics. And there was a very clever paper written by Michael Sale and his colleagues in the Nature a few weeks ago. Was the Nobel Prize for Physics? Yes. Not that it matters. And in this paper, they give some data-driven demonstration that it influenced very much the physicist community. There is another debate. I belong to the international community of the neural network people, and it is always why Hopfield and Hinton got only and why not the others. Obviously, in a field, there are a dozen of people who deserve for this Nobel Prize, and the list of people who believe that they should have got the Nobel Prize is much longer than the list of the actual winners. And so that is obvious that until recently, the Physics Nobel Prize has been used to award traditional physics and impacted physics only. And this year, however, shows the prize has caught up with reality, recognizing interdisciplinary discoveries. But look, the Nobel Prize was founded 120 or 30 years ago, 20 years ago, and that was at different times. And we have the traditional disciplines established 150 years ago, physics and chemistry and biology, but this is a different world. we live in the science, in the science, and there is a lot of interaction among fields, and I do believe that since we don't have any Nobel Prize for the interdisciplinary science, and some people argue that we should need, that somebody should give the financial basis to establish one more Nobel Prize. And so we are not in the position just simple professors of, in a liberal art college. And I would like to speak about the historical background, how this whole industry started. And so in this picture you see Walter Pitts and his boss, if I may say that way. They were not in a very formal connection, Warren McCulloch. Warren McCulloch was one of the founding fathers of the fantastic interdisciplinary movement called cybernetics, together with Norbert Wiener. And Walter Pitts was born in Detroit, and good, not good, he escaped from the house of the parents, spent the nights and days in the parks of Chicago, found somebody who was called Bernard Russell, and turned out that they discussed logic, and Bertrand Russell and Rudolf Carnap, the founder of the Viennese Circle, thought, look, there is Warren McCulloch, who is a neuroscientist, psychiatrist, philosopher. And he believes that the brain implements logic. And you know logic, so why don't you work together? So they published a paper in 1943. Pitts was not yet 20 years old when this seminal paper was published. And that time, Warren McCulloch was interested in real neurons. So what do you see here? Let's see how the pointer works. This is a biological neuron. There are the dendrites which process information, and there is the soma and the axon. So this is if you use the computational terminology, there is an input-output device. And here what you see, how they establish the formal model. So what you see here, neurons are multi-input devices, which means there are many neurons which send synapses to the postsynaptic neuron. And there is a single output. And the single output, basically binary, which means a neuron either produces a signal, generates a signal, or remains in silence. And it is a threshold device because we can calculate the output, which is binary, so 1 or 0, if the weighted sum. Why weighted? Because we don't have to assume, there is no reason to assume that the efficacy of the different inputs are the same. So there is some weights. So that if the weighted input is larger than a threshold, the output is 1, otherwise 0. Now we have a number of neurons which forms a neural network. The state of a neural network is described at a fixed time by a series of zeros and ones. So this is a binary vector. And the dimension of the vector is nothing else than the number of neurons of the network at a certain point. Now, however, if there are inputs, then there is a change in the state of the network. So there is a dynamics of the neuron. There are two possible strategies. If you have a network, we can update the states synchronously, which means that the state of all neurons are changed in the same time, or asynchronous way, just one individually. So serial versus parallel processing. Will it help? So the McCulloch-Pitts model, that was this is the big starting point, everything what we see now in machine learning based on neural networks. So they introduced the formalism, and the generalization led to the notion which called finite automata. I skipped that relationship, but it's called computability theory. And that was build a model to connect structure, function, and dynamics of the models. And very ambitiously, that was the first computational theory of brain and mind. Maybe more importantly, he motivated John von Neumann. Hopefully, many of you know that he is considered as the father of the modern computers when he designed the logical architecture of the nervous activity. So what you see here are the inputs, the weights, the neuron, and this is some function of the weighted sums. So they were interested in implementing logics. So there are elementary logical operations, and, or, exclusive or, nor, and others. And I don't go there, of course, into details, but they were able to build logical gates based on the neurons. Now, this is one neuron, and one neuron, and you can build a neural network. So neural networks are also computational devices, if you wish, an input-output device. So what we see? We have an input vector, we have a weight, that is a weight matrix, and the output is somehow generated by combining the inputs and the weights. If you don't know better, then it's a linear combination. But of course, many times the neurons are not linear, so we should use also some nonlinear functions. So we have also what is called expected response or target. If you give an input and there is an expectation, what should be the answer? Now, what's happened when you learn and there is a supervisor who asks? Occasionally we make mistakes, and then we get some feedback. You should do something different. So we're able to calculate the error. If you have only zeros and ones, then the target should be 1 and 0. So we might say that we might make two types of mistakes. Number one, a neuron fires. It means the output is 1. If it should not fire or remains in silence, so the output is 0 when it should. So there is a difference between the actual output and the expected value. Frank Rosenblatt built what is called a learning machine, adopting what we call supervised learning algorithm. There are different learning algorithms. I mentioned here the supervised learning algorithm because we say, this is the output, this is the expected output, you should make some change. How to make these changes? And that was expressed in the algorithm that he built and famously called the perceptron. That was around 1960. This is a learning machine. So what do you see? You have the inputs, and these are the input layer, and these are some kind of output layers or hidden layers. So I told about the possible mistakes. So we calculate the error. The error might be 0, that is good, answer is good, or might be -1 or +1. So how to teach if a neuron fires, but it should not, too much weight, reduce the weights. So you calculate, this is the old synaptic weight, this is a new one. Take the difference, it might be, the sign might be positive or negative. This eta is just the learning rate multiplied with the input. And I skipped the technical industry with the bias nodes. And so this So what happened? So what is really the goal? We have data and we have the target. These are the inputs. And the perceptron algorithm tries to find, this is very important what I tell now, a straight line to discriminate between the behaviors. So I told you that they wanted to connect neural mechanisms and logic. I believe that many of you knows that it is a true stable. We have two inputs, and then there is a target. So what is it? If you want to describe the logical operation called OR, means a neuron fires if at least one of the input is 1, otherwise 0. So the truth table tells 0, 0, 0, and for all the three combinations, 0, 1, 1, 0, 1, 1 is 1. So 0, 0, 0, this is 1 quality, and here are 3 points, these are the ones. Now, can we discriminate between 0 and 1? Easy. We can do it with a straight line. And of course, there are many straight lines, and this is a different question. What is the best discriminatory straight line? This belongs to a more advanced part of the neural network learning rules called the support vector meshes. I don't speak about now. So perceptron works if the cases are linearly separable. Look, what do you see here? Then you can find a straight line, so you are able to discriminate. This is a discriminatory line between the two types of patterns. What is here? That is not linearly separable. And so there was something which was very strange in the history of science. Look, this is the XOR. You remember, exclusive OR. Exclusive OR means if at least one of the input is 1, but not both. So the truth table tells 0, 0, of course 0, 0, 1, 1, 1, 0, 1, but here 1, 1 gives 0, because this is the exclusive OR. It cannot be 1. Only one of the inputs should be active. So if you put here, then you have 0, 0 is here, 1, 1 is here. So these 2 points are together, and these 2 points are other. Can you draw a straight line? If you can, you will get the next Nobel Prize in neural network. And so you can't. Minsky and Papert, very influential persons from MIT, wrote a book in 1969 about perceptron. XOR is not linearly separable. So the perceptron algorithm in this case does not converge. Neural networks are stupid. You don't have to give financial support for neural networks. It worked. For 15 years, there was no funding for neural networks, which doesn't mean there was no real neural network research. One other approach came from physics, and people worked on spin glass models. Spin glass is a metal alloy where iron atoms, for example, are randomly mixed into a grid of copper atoms. Each iron atom behaves like a small magnet, or spin, which is affected by the other magnets around it. In a spin glass, they are frustrated if there are two parallel state up spins, and have difficulty choosing which direction to point. So that was a spin glass belongs to a family of disorder systems. And just 3 years ago, Giorgio Parisi, the Italian physicist, got the Nobel Prize basically for understanding, to give a mathematical formalism of disorder system. But spin glass was a good analogy, and Hopfield, who was a hardcore physicist at the beginning, adopted the spin glass theory to neural networks. So you see here, zeros and ones in the spin, up and down. And on the same way, binary neurons have two states. So he wanted to solve a problem that you will see on the next slide is related associative memory. So he made a construction. Models are constructed. Here are, of course, just 5 neurons you don't have to take seriously. What do you see here? That is a fully connected network. Each neuron is connected to all of them. And there is one more strict assumption. Wij is equal to Wji. Technically, the matrix of the connections is symmetric. That everybody knew that is both the full connectivity and the symmetric matrix is not plausible neurally. So neuroscientists thought, yeah, it's a good game, but nothing to do with neuroscience. Others thought that still that is something relevant. So if you want to calculate, this is the weighted sum of the inputs, this is the age, and now there is an updating rule. If the age for a specific neuron is positive, then it's +1, otherwise -1. So this is a binary polar neurons. There is another convention which uses +1 and 0. There is some technical reason why the learning rule is simpler for bipolar neurons. And there is a learning. Learning rules are going back, I should have mentioned, but I decided not to bring too much psychology. Donald Hebb, a Canadian psychologist, thought if 2 neurons fires together, then is a tendency to increase the strength between them. And basically, Hopfield also adopted a conjunction rule, xy and multiplied by xj. This specifies a matrix element. If you wish, if you took linear algebra, basically, you should take the outer product of it first. So Hopfield wanted to build what we call auto-associative memory. This is an auto-associative memory when you can recall the whole from a part. So this is a noisy cue. It has two. So the whole learning strategy has 2 elements. First, you should teach. This is letter T, and these are the basic. So you see, so these elements are ones, all the other elements are 0. Now, are you able to find how? Yes. From noisy image, you can reconstruct the whole full part. How? Under the assumption that Hopfield made, full connectivity and symmetric matrix, it is possible to assign an energy or energy-like function. What do you see? You see here are local minima of the energy. Now, this is an energy volume. What's happening if you put here something? Obviously, goes to the local minima, from here to go here. So under the structural assumption, there was an energy function which was defined as the Wixixg, and the local minimum in the energy function is a stable state for the network. So this is the recall phase. Any point from the basin, this is the basin of point attractors, converge to the fixed point. So Hopfield model is restricted to point attractors. And there are other extensions. We know that the real neural system shows oscillation and chaotic attractors, strange attractors. And so this is an extended theory, but the Hopfield model is not able to grasp. I might mention the name of Walter Freeman, who died now maybe 8 years ago, who argued that chaotic attractors are very important in the neuroscience. But I believe it's not really neuroscience. And Hopfield catalyzed the flow of physicists to neural network research and gave a model for associative memory, and a new field was built, physics of neural networks, and established the concept of computation with attractors. John Hopfield, with his close colleague David Tank, wrote a number of papers and showed how the Hopfield model is able to solve combinatorial optimization problem. There is the famous traveling salesman problem. There is a salesman who should visit a number of cities, and there is a best optimal strategy. What is the series of cities? But it is a combinatorial problem. If you have to visit not 3 but even 10 visits, this problem is already combinatorially very difficult, and if you have 50 cities to be visited, it's very difficult. I believe that the whole Hopfield model and his contribution led to the separation of two fields. Number one, artificial neural networks, biological neural networks, and computational neuroscience started to build. And if we build artificial neural networks, it's not necessary to use neurally plausible algorithms. What is this figure? Do you know there is the Scholar, Google Scholar, which shows the annual citation of scientists, and what you see is that is an astonishing stationarity during the 25 years. So still is with us and always attracts a huge number of papers. With the early papers don't get so much citation, the new ones. That these two papers, the pioneer papers, were published in 1982 and 1984, so before the internet. So therefore he got probably 10 times less citations than Hinton, but it means that it was in some sense too early. And interestingly, a number of very good theoretical physicists went to neuroscience, and they spent there a couple of years there. So it's not an accident. Hopfield got the Nobel Prize in physics, obviously not in physiology, because his model was admittedly not neurally plausible. So far, so good. Then I will switch to speak about the Boltzmann machine, which is an extension of the Hopfield model. And so the second paper, Hinton had a paper on discrete Hopfield models, one in continuous Hopfield models in 82 and 84, and a year later, Geoff Hinton and Terry Sejnowski, for many years the editor-in-chief of the MIT Press journal Neural Computation, wrote a paper, introduced Boltzmann machine. Ludwig Boltzmann, one of my heroes, is from Vienna, is one of the founders, what we call statistical physics. Statistical physics is a fantastic field which connects the micro and the macro world, and he managed to express the function what we call now entropy in terms of microscopic state, and also described, helped the transition from deterministic physics to stochastic physics. So, to adding randomness to computation, and randomness is not bad. We don't have to worry, randomness is noise. It might have very good properties. So, they had a new architecture. You see blue and white. There are so-called hidden layers and visible layers. The figure doesn't show well that the visible units, they get direct input from the environment. The hidden units are hidden because the external world doesn't see it. There is no direct input to them. But here, in this construction that was preserved the full connectivity of the Hopfield model. So in the deterministic model, you know exactly what is the state of the city, what is the state of a system. Here we speak what is the probability that a system is in a certain state. So we need probability distribution instead of fixed patterns. So the Boltzmann machine is nothing else, which is one of the big achievements of Hinton and Sainosi, the Hopfield network plus the hidden units and the stochastic transition. And so far so good. So they adopted the Boltzmann distribution, the probability that the system will be in a certain state as a function of the state's energy and the temperature of the system. And so maybe I don't go all the technical details, but the probability, that is the change in the energy, so between A2 minus A1, is exponentially depends the energy difference divided by a number that we might call temperature. And we have the partition function that is very famous in statistical physics. So somehow, using this probabilistic strategy, you can update the state of the neuron calculating the energy with probability based on the energy difference for x, y, plus minus 1, using a sigmoid function, something here what you see. I took it from the figures of, everybody speaks now in this community about Hopfield and Boltzmann networks, so there are many papers we send each other our slides. So Wlodek Duch is in Torun, Poland, and gave a lecture for the community, the Polish Physical Society, and I used these figures from him. Now I told that and promised that I will speak about the relationship with the Boltzmann machine and the new AI. AI, we hear each day many times. There are two large classes of models: discriminative models, generative models. Perceptron was discriminative. It helped to discriminate between points by using straight line. Of course, in higher dimension, you have a plane or hyperplane. It works not only in 2 dimensions. So it helps to discriminate between different kind of data. Discriminative models are very good to see, this is a dog, this is a cat. So this discrimination. Mathematically, it captures the conditional probability, the probability of y assuming x. The other class, which also belongs, which is also used by a somewhat controversial movement called AGI, Artificial Generative Intelligence, generative models. So we can generate new data and new data instances. And this is what is very dangerous. Could generate new photos of animals, not animals, that look like real animals. Mathematically, they capture the joint probability, or if there are level-free data, then just the bx, no levels. So the Boltzmann machine was good, but it turned out was not sufficiently efficient. And then Hinton thought, we don't need connections within the visible layers, we don't need connections within the hidden units, and established a more efficient training algorithm. Surprise, it worked. And that is what we call the so-called restricted Boltzmann machine. This is a mistake. So no connection between the visible and the hidden layers, more efficient training algorithm. Now many applications emerged, and you will see how many citations here. Data have a huge dimension, so dimensionality reduction is very important. we have the old classification problems, but not only for static data as image processing, but it's very difficult speech recognition. So input with continuous time. I didn't explicitly mention the Hopfield model is able to learn only static patterns. I show you, you know it now. But what is interesting was in olfaction. This is a continuous input, speech, and this is continuous input. It's able to classify. The restricted Boltzmann machine was very successful to apply in regression, which is analyze the relationship between variables and the predict outcomes. Collaborative filtering. That is what the recommendation systems use. Everybody uses each day recommendation systems, where to travel, where to have the holiday, restaurants, lectures, whatever. Collaborative filtering. Predict user preferences based on their past behavior or based on the behavior of your friends who are also did something similar, and recommended items that are likely to be in interest of the user. You see that you put a Netflix movie, look the next one. Feature learning. And it predicts user preference, feature learning. And automatic process that helps machine learning models identify and optimize patterns from raw data to enhance performance. And the huge industry behind what is called topic modeling. So groups, words that appear together and frequently across documents to identify distinct topics. I gave this stupid example. If you did in a text, Manchester, Barcelona score goal, that's probably a soccer-related article. And so there is a bag of words, and how to make implications from using this bag of words to see. And one more element, which was again controversial. So, but Hinton did together with Romelhart, died very early, and Robert Williams in 1986. So you see these old results are almost 40 years old. Feed-forward network means input networks, hidden network, output network. There is a unidirectional information flow. So for the hidden layers could be trained for classification using what is called back propagation. Some error goes back. And then it was, no, it's neurally not plausible, but very efficient. Now people came. One of them was Paul Verbeuss, also a director of the NSF. It turned out that he published this algorithm in 1974. And then not in a small university, it was a PhD at Harvard, but still it was too early. Nobody was interested in it. Still he writes, just I read his mails, I was among the 20 people who said, okay, I'm sufficient old, I'm able to accept, he wrote, but still we know very well that he published this dissertation, basically this algorithm. But you should come in a good time and should be popular. It turned out even earlier, Marlon Linnainmaa wrote a master thesis in Finland, in Finnish language. Who cared? So, in order to get the Nobel Prize, probably you shouldn't write in Finnish or in Hungarian. It's a good idea to write in English, which is not a problem in this country. And, but this backpropagation algorithm was very important. For the newer developments, I mentioned that the generative models, what can do, generate or fake examples. And that is what people started to worry. How we are able to make classification between real and fake. And so generative artificial intelligence tools allow anyone to quickly and easily create massive amount of fake content. But there is no medicine against development. I don't believe it can be forbidden. Probably everybody heard that is a buzzword, deep neural networks. Deep means there are more layers. So first perceptron had one input output. Then there was the feed-forward networks, input layer, hidden layer, output layer. Gosh, if we build more layers, it helps better. And deep neural networks uses more complicated architectures and somewhat changed learning rules that are full of applications for healthcare, image recognition, cancer detection is obviously very important, autonomous vehicles, and e-commerce recommendation systems, many, many others. And I don't know whether good or bad, so that is art. So there are, OpenAI has a series of programs, DAL-E2 now they have AC. Text to image. So the input is a painting of a unicorn typing on a laptop. And so this is the output. This is art. I don't know. This is what we have now. Should we be happy that we are able to build? I believe that is, in any case, an achievement, and this is what generative AI can do. As concerns Hinton's intellectual fingerprint, you see he has an incredibly large, so 10 times larger citation number than Hopfield, and ImageNet, so classification of image with deep convolutional neural networks. This only paper has 160,000 citations. There is a review paper in Nature about deep learning, all close to 100,000 citations. It's incredibly large numbers because everybody is now on this industry, maybe too many people, and so Hinton was very efficient. This is the deep learning paper. Deep learning allows computational models that are composed of multiple processing layers to learn representation of data with multiple levels of abstraction. And these methods have dramatically improved the state of art in speech recognition, visual object recognition, object detection, and many other domains such as drug discovery and genomics. Deep learning discovers intricate structure in large data sets, so structures in large data sets, by using the backpropagation algorithm that I mentioned previously to indicate how a machine should change its internal parameters that are used to compute the representation in each layer from the representation in the previous layer. Deep convolutional nets have brought about breakthrough in processing image, video, speech, audio, whereas recurrent nets have shown light on sequential data such as text and speech. And what you see here, without going to the details, there are more hidden later, hidden later too. No, you can build some more hidden layers. So at a certain point, and I think that many of you heard Hinton, gosh, it's too much. So he is occasionally called the godfather of AI, leaves Google when he spent about a decade and words of danger ahead. And so now he worries it will cause serious harm. John von Neumann, the father of the computers, told that, can we survive the technology? He wrote this paper in the mid-1940s. He told, we cannot tell that you cannot do science, and but we might hope that the humans will bring intelligence decisions. Now, from deep mind, there is the deep mind, and I finish my lecture by telling you that not only the physics, but the Nobel Prize in chemistry also went to people who are working for the deep mind, but it's a different story. I'm speaking about physics today. Thank you.
Does anyone have any questions?
Well, first of all, thank you, Dr. Erdy, and thank you for hosting the event. I do have a question about
I believe it would be good to come here to get the mic.
Go ahead.
Thank you. I do wanted to know that the topic of neural networks, I think it's really interesting, but it has come before, and it has come into mainstream for a long time. Why do you think that it's only until 2024 do we actually see it getting recognition at the Nobel level? Thank you.
I'm not in the jury of the Nobel committee, so I'm not sure. I believe that Hinton and Hopfield was revolutionary and contributed very much to this field. Whether or not it's physics or not, I leave it for the community to discuss.
Thank you.
Any other questions?
Okay. I think my biggest question was when you were talking about the Boltzmann machine and the Hopfield model, like, what is kind of the big difference? Because do they both have the stochastic sort of like randomness, or is it just one?
Yeah, Hopfield is purely deterministic, and Boltzmann used the stochastic method. Additionally, for the restricted Boltzmann machine, there were no connection between the within the layers, and they had another more efficient learning algorithm. So it turned out that with relatively small changes, there were huge differences in the efficiency of the algorithms. And it turned, we are able to do image segmentation with this method, which was very, very important.
So, I think my question is connected to the question which was asked before. We are seeing a lot of large learning models like ChatGPT. Do you think this technology should have come earlier, or is it late? Or is it too early for technology like ChatGPT?
I didn't want to go to technical details. I'm not very familiar, but I know that the so-called transformer model and the attention model were used for the large language models, and obvious they are the outcome of this whole industry which grew up from McCulloch Pitts models and the perceptron. So I do believe that we should give credit for the early pioneers, and still almost everything is the same. A little different architecture, a little different learning algorithms, but the result is dramatically different. So small changes in the model, large changes in the applications. I might be wrong, but this is my feeling.
But do you think this technology should have come earlier, like ChatGPT, or is it too early for humans to?
No, it's right. We should learn. We should learn and use, and I don't mind if the students use it. We should live with it. If the technology develops, we can't do anything else. We should find out the rules. So I don't necessarily encourage students to use it instead of using their own mind, but we should be able to learn with it, to live with it.
All right, thank you guys all for coming out. If you have any questions, I'm sure Dr. Erdy could answer them if you want to come forward and ask, but otherwise, thanks for coming.
Thank you.